Greetings and welcome to Distillate. In the previous class, we discussed how to form a material balance equation and solve a material balance problem. So in order to solve a material balance problem, we have to read the description mentioned in the problem and we have to make a block diagram which comprises of units. So let's say this is our unit and this is my input stream with F1 as the flow rate, mass flow rate or mole flow rate, and F2 as another input stream with F2 as the mole flow rate or mass flow rate, and P as my product stream. And then let's say mass fraction of some component in, let's say this feed stream has A and B, then mass fraction of A in F1 is X1 and mass fraction of A in F2 is X2 and mass fraction of A in P is X. All right. So in that case, we can form we can form three equations, or we can say we can form minimum two equations, and then we can form equations based on the number of components, right? So for example, here we have two components, so we can form two component balance and one overall balance equation. So we can form an overall balance equation. So overall balance equation does not consider composition. It only requires the input and output streams. So this is my first equation that I can make. And the second equation, or the next n equations I can make depending on the number of components. So if I have two components, I'll make two component balance equations. So over here, I have two components. Therefore, I'll make equation number 2 with balancing component number A. So x1 f1 plus x2 f2 is equal to xp. All right. And the third equation I'll form by balancing component B, which is 1 minus x1 f1 plus 1 minus x2 f2 is equal to 1 minus x into P. So this is how I'm going to make my component balance equation. Then we also discussed that how to deal with multiple units. So if we have more than one units, let's say I have this as well as another unit. All right. And then there is an internal transfer over here. And let's say this is my F. This is F1. This is F2. This is P1. This is P. Here it's going to be X1. Sorry. Let's call it XF over here. Then this is X1. This BXP1. This BXP2. Sorry, I'm sorry. This would be X2, not X2. This will be X2. You can give any representation to these variables. I'm just giving it to make it less confusing for you. All right. And this I'll call it as XP. So this is my representation. So for dealing with a problem like this, what we are going to do, we are going to consider a system boundary, which I called it as a control volume. So I'm going to take a boundary. I'll enclose this entire system into a small boundary. All right, I'm going to enclose this entire system into small boundary, which is my control volume. All right, and then I will consider this green box as my only unit. All right, I'll consider my green box as only unit, and I'll see that what all streams are being transferred from surroundings to this box or from this box to the surroundings. All right, so you can see this P1 stream, it is being transferred from 1 to 2, right? Therefore, we are just going to eliminate P1. We are not going to include P1 while we are doing material balance over here for this unit. So with here, we'll have F, then F1, F2, and P. All right. This P1 has not been considered because it was inter-unit transfer from unit 1 to unit 2. Therefore, when we are going to make our equations for this particular unit, then we are going to form the overall material balance equation for the green unit. So overall equation that I'm going to form is going to be F plus F1 plus F2 is equal to P. That is my equation number 1. And when I'm going to do component balance, then I'm going to form the equation XF into F plus X1 into F1 plus X2 into F2 is equal to XP into P. All right. This is the second equation that I have formed for component balance. All right. If I need more than, if I have more than one variable, more than two variables, then I can form more than two equations by balancing the second component as well. All right. And then another method of doing this problem is by taking individual units. By taking individual units and doing material balance about those units. For example, over here I have two units. So I'm going to take unit 1 and unit 2 individually, separately, right? And then I'm going to do material balance. So for unit 1, my input is F, then F1, and P1 is going out, right? And then for unit 2, my P1 is coming in, as you can see. F2 is as well coming in, and P is going out. So we are going to form material balance equations for unit number 1 as F is equal to, F plus F1 is equal to P1. That is for the overall material balance. And the component balance equation is going to be XF into F plus X1 into F1 is equals to XP1 into P1. Right? This is my component balance equation. And similarly, I'm going to make two equations for unit number 2. That is input, overall material balance, input is equal to output. P1 plus F2 is equal to P. And second is XP1 P1 plus X2 into F2 is equal to XP into P. So this is my second equation that I've formed. So based on these equations, I can find my result. All right. So this is how you deal with more than one units. All right. You take a control volume, you do overall material balance about that, or you take separate units and you do material balance about those. All right. Now we come to a very important section of chemical process calculations, that is material balance without chemical reactions. All right. So in this particular section, when we'll be dealing with material balance without chemical reactions, so in this section, we'll be dealing with different unit operations, and we'll be keeping in mind that there's no chemical reaction that is taking place. All right. So in the previous class, I discussed the mass balance equation, general mass balance equation with you all. Input minus output minus accumulation minus generation, plus generation is equal to consumption, right? This is the equation that I discussed with you all. Or I guess accumulation was this side, but it's the same equation overall, right? So input minus output minus accumulation plus generation is equal to consumption, right? Now, since this is without chemical reactions, therefore, generation term and consumption term is going to be 0. All right. Also, we are going to keep steady state throughout. All right. This course, we are going to deal with steady state only. So therefore, accumulation term is going to be 0. Hence, the final equation that we are going to get is input equals to output. This equation, this mass balance equation, we are going to use. So material balance, whatever we have been doing so far, we will be doing all those things, the same thing that we have discussed in the last class. It's that simple. We only have to form equations and we have to get the result. But there are certain special cases for special unit operations. For example, if you have a crystallization, then you have how to calculate X for crystal and so on. So we'll be discussing those conditions over here, and then we'll be dealing with problems. While before you're studying this particular topic, material balance without chemical reactions, make sure that you're very clear with whatever was discussed in the previous video. All right, in the last video, whatever I had discussed, how to solve material balance problem, how to make a block diagram, how to make equations, how to solve these problems. Please make sure that you're clear with all those things before you're starting with this section, because this section involves only making equations and solving the problems. All right. So now we come to different unit operations that are involved in chemical industries. So whenever we are talking about chemical industry, it involves a variety of unit operations. All right, it involves a variety of unit operations. So a few of them I have listed over here. So mixing. In mixing, we simply have A and B are fed to the mixing unit to form a mixture. So this is my mixing unit. I will feed A to it, I will feed B to it, and I'll get a mixture. So that's what happens in mixing. Then we have evaporation. Solution of A and water is fed to the evaporator. So if this is my evaporator, then I'll feed A and water, a solution of A and water, to the evaporator. Is fed to the evaporator, and water is evaporated, leaving behind concentrated solution of A. So some of the water is evaporated, and the remaining we have concentrated solution of A, because some of water has been evaporated, so we will be left with concentrated solution of A. Then we have distillation. Mixing is adding A and B to form a mixture. Distillation is getting A and B from the mixture. All right, so mixture, so distillation comes under separation processes, one of the separation processes. So that's distillation. So it's basically a mixture of A and B is fed to the distillation column, and a mixture with A in abundance is obtained. Usually we try to get pure A, but it's not possible to get 100% purity. So we get A in abundance from the top. All right, while a mixture containing B in abundance is obtained from the bottom. So if this is my distillation column, and this is whatever I have fed the mixture, then from here I'll get the abundance of A, and here I'll get abundance of B. In crystallizer or in the crystallization, solution of A is fed to the crystallizer unit, and crystals of A are obtained along with the remaining A in the solution. So if you have this as the crystallizer and I feed a solution of A to this, then you'll get crystals here. All right, you'll get crystals here, and remaining, whatever A is remaining, that comes out over here. All right. Then drying. In drying, we have wet solid. Remember, in drying, we have wet solid. This wet solid is made to pass through a dryer. Okay, so this gives us dry solid, and again, water is removed. Then we have absorption. Absorption is where, again, absorption is a separation process. So here, a mixture of A and B and a pure solvent C is passed into the absorption unit. So if this is my absorption unit, then I have a mixture of A and B, and I have a pure solvent C. Now the solvent C is such that it will, as soon as it comes in contact with A and B, it will absorb A. All right, so here you get A plus C. All right, here you get A plus C, and whatever B you have plus whatever A is remaining. Okay, whatever A is remaining, that is obtained from the other stream. All right, so C, it absorbs A. So this is basically used to separate a mixture of A and B. All right, then extraction is again same as absorption. Extraction and leaching, these absorption, extraction, leaching, these are all the same process, just phases are different. For example, when the mixture fed to the absorption unit is liquid, it is known as extraction. So generally this absorption is basically your gaseous mixture. It has a gaseous mixture, and you have C. C is the solvent, so C will absorb the gas A in it. All right. So that's done usually in, for example, in carbon dioxide manufacture process. So there, carbon dioxide is absorbed. Carbon dioxide is absorbed from the flue gases, and the rest of the flue gases are removed, and then the carbon dioxide is separated. So this is one of the units that is used over there. Then in extraction, the mixture that is fed is liquid. All right, in extraction it is liquid. So instead of gas mixture, you have a liquid mixture. That's all. That's all. The rest of the principles, they remain the same. All right. And in leaching, whatever you have is solid. And the mixture fed to the absorption unit is solid. It is called leaching. This leaching you can observe in tea bags. So in tea bags, that is basically leaching process, where you dip the tea bag in water. So water acts like a solvent, and the chemical that is inside tea bag, whatever the tea, the flavor that is present inside tea bag, it is extracted. It is extracted by water. So that is basically leaching process. All right, that is leaching process. All right. So then we come to the first very important unit operation, mixing. So in mixing, we basically have different streams which may have same or different compositions. They are fed to the mixing unit with output as a single stream with a certain composition. All right. So let's say if this is my stream 1, F1 with composition with mole fraction X1, and F2 with mole fraction X2, and this is, let's say, P with mole fraction X, then I can form my material balance equation. Overall material balance, F1 plus F2 is equal to P, and component balance as X1 F1 plus X2 F2 is equal to Px. All right. So this I can do for mixing unit. All right. So that's all about mixing unit. So let's do problems based on the mixing unit. So a concentrated solution of sulfuric acid has to be diluted by adding water to it. A 98% solution is diluted to 50% by adding water. All right. If the solution comes out at the rate of 1500 kilomole per hour, find the molar flow rate of concentrated acid and water fed to the mixing unit. Now you have the question in front of you. Pause the video and try to solve this problem yourself. Hope that you could solve this problem yourself. But if you haven't been able to solve, then let's have a look at it. So first of all, as I told you, first step to solve a material balance problem is to draw a block diagram. So let's see what block diagram can be drawn for it. Concentrated solution of sulfuric acid has to be diluted by adding water. 98% solution is diluted to 50% by adding water. So we are mixing basically solution, sulfuric acid and water. So I'll draw a block diagram of the mixing unit. All right. I'll draw a block diagram of mixing unit. And I'm going to take sulfuric acid over here, and I'm going to add water from here. Let's right. So sulfuric acid stream, let's call it S, and water stream, let's call it W, and the dilute sulfuric acid stream, let's call it D. All right. So they have given that 98% solution, that is XS, is 98%. Does water contain sulfuric acid? No, it's going to be pure water. So XW is equal to 0 because it has no sulfuric acid. It's pure water, right? And is diluted to 50% by adding water. So XD is 0.5. Okay. If the solution comes out at a rate of 1500 kilomole per hour, that means D is 1500 kilomole per hour. All right, D is 1500 kilomole per hour. We don't know S, we don't know W. So let's form equations. The first equation we are going to form for overall material balance. So when we form an overall material balance equation, we get S plus W is equal to 1500. Equation number 1. Second equation we are going to form for component balance. So component balance equation, is XSS plus XWW is equal to XD, right? Now XW is 0, so this entire term becomes 0, hence we get 0.98 S is equal to XD is 0.5, D is 1500, hence S is going to be 0.5 into 1500 upon 0.98. All right. So on solving, when we solve this particular equation, we get sulfuric acid S is equal to 765.3. The unit is going to be same as D. All right. Unit is going to be the same as D. All right. Then using the first equation that we formed, we are going to find W. So W is nothing but 1500 minus S. S is 765.3. Hence, W is going to be 734.7 kilomole per hour. All right. So this was all. That was the solution for example number 5. Right. So now hopefully you people have understood that it's all the same. You only have to form equations and solve problems. All right. You only have to form equations. Just once you get equations right, rest nothing is a problem. So the main part of a material balance problem is forming equations. All right. So let's go to example number 2. 1000 kg of mixed acid of composition 40% H2SO4, 45% HNO3, and 15% H2O is to be produced by strengthening waste acid of composition 30% H2SO4, 36% HNO3, and 34% water by weight. Concentrated sulfuric acid of strength 95% and concentrated nitric acid of 80% are available for this purpose. How many kilograms of spent acid is basically waste acid, and concentrated acids are to be mixed together? So go ahead, pause this video and try to solve this equation yourself. Hope you could solve this problem. If not, then let's have a look at the solution. The first step is again to draw the block diagram. So I'm going to keep the mixing unit here. This is my mixing unit. All right. Then I'm going to add I'm going to add waste acid, sulfuric acid, and nitric acid. So this is going to be my waste acid. Let's call it W. I'm going to add sulfuric acid. Let's call it S. And I'm going to add nitric acid. Let's call it N. All right. And based on that, I'm going to form mixed acid. Let's call it M. All right. So now there are more than 2 components. There is sulfuric acid, there is water, and there is nitric acid. Right. So I'm not going to write XW, XN, nothing like that. I'm just going to write the percentages over here so that you people are not confused. All right. So we have waste acid as 30% H2SO4, 36% HNO3, and 34% water. So 30% sulfuric acid, then 36% nitric acid, and finally 34% water. All right. Then sulfuric acid is 95% concentrated. So we are having 95% sulfuric acid. And then nitric acid is 80%. So 80% nitric acid. Okay. This 95% and 80% means 5% and here it's 20% water, right? So it's 5% water and here it implies it's 20% water. All right. And the product that we get is 1000 kg. So M is equal to 1000 kg. All right. And 40% H2SO4. 45% nitric acid, and since it's 45% and 40%, therefore water that we are going to get is going to be 15%. All right, this is my block diagram. Hope you people have got this block diagram. All right, if you people could not draw this block diagram, please go back to the previous videos and make sure your fundamentals are clear. All right, I've taught how to draw a block diagram. I've given all the steps. So please make sure that your fundamentals are clear before you attempt these problems. All right. So then we go ahead to make the overall material balance equation. So the overall material balance equation, we are going to put input, that is W plus S plus N, that is your input, is equal to output. Output is 1000 kg. So M is equal to 1000 kg. Equation number 1. All right. Then we come to component balance equations. So there are 3 components and we have 3 unknowns, W, S and N. So that means we already have 1 equation. We need 2 more equations. So we'll do 2 component balances, right? So we are going to balance sulfuric acid. I'm going to balance sulfuric acid. So sulfuric acid is present in this. It is present in this, but it is not present here, right? So the equations that I'm going to form is 0.3 W, because it's 30% sulfuric acid, plus 0.95 S, because it is 95% sulfuric acid, plus 0 N, because there is no sulfuric acid here, right, is equal to, it's 40%, right? So 40% H2SO4, therefore 0.4 into 1000. Equation number 2. All right. And then I'm going to form an equation for nitric acid. So nitric acid is, I'm going to balance nitric acid. So nitric acid has 36%, you have 36% nitric acid. So in waste acid, so 0.36 N. Then in sulfuric acid, you don't have nitric acid at all. So it's 0 S, plus nitric acid is, in this particular stream, there's 80% nitric acid, so 0.8 N. And in the acid that is produced, we have 45% nitric acid, so 0.45 into 1000. Equation number 3. All right. Now there are these 3 equations. So these can be solved, either you can directly use your scientific calculators for solving these equations, or you can use the simple matrix method. Ax is equal to B, hence x is equal to B, A inverse of B, right? Where matrix A is going to be 1, 1, 1, that is coefficients of the first equation, then 0.3, 0.95 and 0, coefficients of the second equation, and 0.36, 0 and 0.8. All right, that is going to be your matrix A. Then to find out its inverse, you have to use 1 upon determinant of A times adjoint of A matrix, right? That's how you get A inverse. And then matrix B is going to be the matrix of all the coefficients, all the constant terms. That is, for the first equation you have 1000, for the second equation it's 0.4 into 1000, that is 400, and for the third equation it's 0.45 into 1000, that is 450. All right, and X is the variable matrix, that is of course going to be W, S and N. So on solving, you get W, that is the waste acid that is present. So W, you will get a 70.225 kg. All right. Then you will get S, sulfuric acid added, is 398.876. And finally, N, that is nitric acid atom, is 530.899 kg. So hope you people could get this answer using any of the methods for solving equations. All right. Then we come to the next unit operation, that is evaporation. Evaporation is basically, as I told you, you have a solution of A and water, and some amount of water is evaporated, and therefore, since water gets evaporated, now you have concentrated solution of A and water. All right. So stream with a certain concentration is fed to the evaporator. Evaporator evaporates some of the water present in the feed and gives out the concentrated solution. Remember, it evaporates only water. Whatever A is present in the feed, that is not over here. So if I say that this is my F, this is my P, and this is my E, and here I have XF, that is mole fraction of A, and here I have XE, mole fraction of A in the evaporator stream, and this is XP, mole fraction of A in the product stream, and XC is going to be 0, right? Because it does not evaporate A, it evaporates only pure water, right? It evaporates only pure water. So remember, so actually it's these things, it's these special cases for each of the unit operations that because of these you have to study these unit operations separately. Otherwise it's the same. You simply need to form equations and solve, right? So that's all. So water evaporates from water evaporated from water does not contain the solute in it. Hence, the mole fraction of water in the evaporated water stream is 1. Mole fraction of water in this stream is 1. Hence, mole fraction of the solute is 0. Usually, the solution fed to the evaporator is termed as weak liquor. Keep this in mind. This is usually termed as weak liquor, and the concentrated solution coming out of it is termed as thick liquor. So this is weak liquor and this is thick liquor. All right. So based on that, let's go on to example number 3. Pause the video and try to solve the problem yourself. Hope that you have managed to solve this problem yourself. If you haven't, then let's go on and solve this problem. So 1000 kg per hour solution containing 10% solids is concentrated to 50% solids. Find the amount of water that has evaporated. So first of all, let's draw a block diagram. So we have an evaporator. This is my evaporator. Then 1000 kg per hour solution. That means my F is 1000 kg per hour. XF is 0.1. P, I have no idea. XP is 0.5. And E is the amount of water evaporated. XE, as I told you, is going to be 0. So based on this, I'm going to make my overall material balance equation. All right, overall material balance equation. So that is input F is equal to output E plus P. F is equal to E plus P. Since F is 1000, so we get E plus P is equal to 1000. Equation number 1. Then I'm going to do component balance. So when we do component balance, then simply solid balance we'll do. Okay. So I'll balance solids. So for solid balance, we have XFF plus XEE is XFF is equal to XEE plus XPP. Right? Input is equal to output. Right? So I'll write this equation once again. It's input equals to output. Therefore, you have XF into F, that is your input, is equal to XC into E, that is your output, plus xp into p, that is another output. Correct. Now since xc is 0, therefore this term is going to be 0. Hence we'll get xf into f is equal to xp into p. Now xf they have given to be 0.1 and xp 0.5. Therefore we get p is equal to xf f upon xp, that is 0.1 into 1000 upon 0.5, that is 200. All right, 200 kg per hour. This is my P. All right, then using my equation number 1, I'm going to get this equation. I'm going to get E equals to 1000 minus P, that is 1000 minus 200, that is 800 kg per hour. All right. Example number 4. Go ahead and try to solve this problem yourself. Hope you could solve this problem. If you haven't, let's go ahead and try to solve it. 5000 kg per hour of an aqueous solution of sodium hydroxide contains 10 weight% of sodium hydroxide, and it is concentrated to 50 weight% sodium hydroxide in a double effect evaporator. A double effect evaporator means that it has 2 evaporators. All right, 2 evaporators. Evaporator 1 and evaporator 2. All right, evaporator number 1, evaporator number 2. Now this is more than 1 units. More than 1 units. So evaporator number 1 and evaporator number 2. So 5000 kg per hour of an aqueous solution containing 10 weight% NaOH is concentrated to 50 weight%. That means whatever goes in is having 10 weight%. So let's call it F. It is 50,000, 5,000 kg per hour. I'll remove a 0. So it's 5000 kg per hour, and its mole fraction is 0.1. Mass fraction, weight% is 0.1. And the product, which we have no idea what P is, but we know that XP, it is 0.5 because it is 50%. It has been concentrated to 50 weight%, right? The feed solution is partially concentrated on the first evaporator and then fed into the second evaporator. So they are saying that some amount of water, partially concentrated as in some amount of water has been removed from the first evaporator itself. So E and XE we know is 0. And then whatever we got, let's call it P1 and let's call the mass fraction as XP1. All right, we have no idea about this too. All right, and then it is fed to the second evaporator. All right, find the amount of 50% of NaOH solution produced and amount of water evaporated, assuming that the water evaporating capacity of both evaporators are same. That means both evaporators evaporate the same amount of water, E. All right. Since water evaporating capacity is the same, therefore we are going to keep both E's as same, E, E. All right. And we have to calculate the concentration of NaOH solution leaving the first evaporator. All right. We have to calculate NaOH leaving the first evaporator. So this is more than 1 unit. So we can definitely do it by making a green box. Right, making a green box. But again, we'll have to do material balance around unit 1. Right, we'll have to do material balance either around unit 1 or around 2 because we need P1 and XP1. So one equation or 2 equations we'll form from the green box, and then we'll switch to either unit 1 or unit 2, depending on whichever way you're comfortable. All right, you can go anyways. So we are going to keep this green box. Again, what is this is my overall evaporator. Okay, equivalent evaporator that I've. Now let's see what is the stream, what is the incoming stream. It's F. What are the outgoing streams? E, E, P. P1 is not counted because it is unit 1 to unit 2 transfer. Unit to unit transfer. Okay. Then we have these values 5000. Then XF as 0.1. Then we have XE equals to 0 in both cases. And XP is 0.5. All right. So we are going to form the equations for green box. All right. We are going to form equations for green box. So first equation for overall material balance. So when we form overall material balance equation, it's F input is equal to 2E, E plus P. These are the outputs, right? So F is 5000. So we'll have 2E plus P is equal to 5000 kg per hour. All right. This is my equation number 1. Then I'll form component, that is solid balance equation. So I'll get 0.1 into 5000. This is my solid balance. Plus, is equal to, since there is no solid in evaporated part, so we'll just write down XP into P, right? So based on this XP, we know it's 0.5. So it's going to be 500 upon 0.5 is equal to P. 0.1 into 5000 is 500. So 500 upon 0.5, that is 1000. P is 1000 kg per hour. All right. Since we have got P, then using the first equation, we get E equals to 5000 minus 1000 upon 2. That is 2000 kg per hour. All right. 2000 kg per hour. Right. Then now we have found E. All right, we have found E. Now let's move on to any of the 2 units, 1 or 2. So I'm going to do for 1. So then I'm going to do material balance for unit number 1. So let me draw the block diagram for unit number 1. If you're comfortable solving using the first block diagram itself, then you can do it that way as well. But I am drawing the block diagrams again and again so that you people are clear. Whoever is not able to understand, he or she is able to get this, right? So about unit 1, again I'll draw the block diagram. We have F, which is 5000 kg per hour. Then we have XF, which is 0.1. We have E, which we have just calculated it to be 2000 kg per hour. And we have XE, which is equal to 0. Out of this, we have P1, which we don't know. And we have even XP1, which we don't know. All right. So the first equation that we are going to make is for overall material balance. So that is input is equal to output, right? So we get P1 is equal to F minus E, that is 5000 minus 2000, that is 3000 kg per hour. This is P1. All right. Then I'm going to make component balance equation, or I can say my solid balance equation. So when we are doing solid balance equation, then I'll have XF into F is equal to XP1 into P1. So that is 0.1 into 5000 is equal to XP1 into 3000, right? So XP1 is going to be 500 upon 3000, right? That is 1 by 6. All right. So we can write this as 0.6. 0.1667. Right? XP1 is 0.167. So that was asked. Find the concentration of NaOH solution leaving the first evaporator. That is 16.67% solids. All right, 16.67% solids. Fine. Then we move on to example number 5. Pause the video and try to solve this problem yourself. Hope you could solve this problem yourself. If you haven't, let's go ahead. This problem involves mixing and evaporation, both. All right. So let's see how to deal with this problem. Two equal amounts of sulfuric acid solutions are added to a mixing unit. One contains 50% sulfuric acid, while the other contains 32% sulfuric acid. All right. The 200 kg per hour solution withdrawn from the mixing unit is added to an evaporator, which evaporates 60% of the water in the solution, and the concentration of sulfuric acid finally achieved. Let's draw a block diagram for this. So when we draw a block diagram, we'll get our mixing unit and we'll get our evaporator. All right. This is definitely going to be E and X is 0, right? Then equal amounts of sulfuric acid solution. So S. One is 50% and the other is 32%. So XS is 0.5 and here XS1 is 0.32. All right. PXP not. All right. And they have given this to be 200 kg per hour. Now, if you try to solve this problem without, considering individual units, if you use the overall control volume approach, if you put this under a control volume and you try to solve this, then it would be tougher in comparison to the solving if you do it unit wise. The reason being that we have got nothing. We don't have S, we don't have E, we don't have P, right? So if we take this particular unit, this green unit, then in that case, we'll have only variables, right? We'll have S, we have P, we have E. So we'll have to make too many equations. Apart from that, if XP would have been known, then we would have still considered, but even XP is not known, right? So we'll get XP into P, right? We'll get XP into P as one of the variables. So this is a very complicated system to solve. That is why it would be easier if you solve using one unit, that is the mixing unit. You solve this first and then you use this green unit. So let me draw the green unit block diagram for further reference. But what we are going to do is we are going to first solve using the mixing unit. So when I draw the green unit, I have S with XS1 as 0.4, right? XS as 0.5, and here I'll have S with XS1 as 0.32. Here I have E with XE as 0. And here I have no information. I don't have P, I don't have XP. Right. So if you try to solve this equation, solve the system, it's going to be very difficult. Right. So what we are going to do is we are going to use the mixing unit. All right. We are going to use the mixing unit. So I'm going to draw the block diagram for mixing unit. All right. I'll draw the block diagram for mixing unit. So I have S. and I have 200 kg per hour solution. All right, so S with XS as 0.5 and XS1 as 0.32. All right, so let's call this as X over here, right? The mixture over here. So when we form overall material balance equation for this, so we'll get S plus S, input plus input, gives you output, that is 200. Therefore, 2S is equal to 200, S is equal to 100. Okay, S is equal to 100 kg per hour. Fine. You got this. Then do component balance. Do component balance. So when you do component balance, you will get 0.5 into 100 plus 0.32 into 100 is equal to X into 200, right? Input of sulfuric acid plus input of another stream, sulfuric acid from another stream, is equal to X into 200. All right. So from here you will get X. From here you are going to get X is equal to 50 plus 32 by 200. Right. So that is 82 by 200. That is 0.41. This is the concentration of sulfuric acid over here. All right, 41%. Okay. Then we go back to this particular block diagram, that is for the green one. And let's see what all values we have now. We have S, that is 100 and 100. We have, do we have anything? No, we don't have anything. All right. So since we have these things, therefore, can we still solve this particular system? Can we still solve the system of equations? No, we still can't, because we again don't have XP or P, right? So we'll have to again make an equation for evaporator unit. All right, so I'm going to make a block diagram of evaporator unit. Where I have 200 kg per hour solution coming in with X is equal to 0.41. E being evaporated, so E and X is 0. And you have, sorry, X is 0 and you have P and X. But now, as you can see, this question, this system, it still can't be solved, right? It still can't be solved because we'll make overall material balance equation 200 equals to E plus P. Then we'll make solid balance equation, that is 0.41 is 0.41 into 200 is equal to XP into P, not solid balance, sulfuric acid balance, right? So still it can't be solved. That means we are missing something. We are missing something in the question. So let's go back to the question and see what is the question demanding from us. So let's read the question again. 2 equal amounts of sulfuric acid solutions are added to a mixing unit. One contains 50%, the other contains 32%. We have used all these informations, right? The 200 kg per hour solution, used this, withdrawn from the mixing unit, is added to an evaporator, which evaporates 60% of the water in the solution. We haven't used this information. All right. So we need to use this particular information. All right. So let's go on and use this 60% of the water in the solution. So what is the amount of water in the solution? What is the amount of water in the solution? Again, we cannot use this diagram to evaluate it. All right. So in order to calculate water in the solution, in the mixture, water in the mixture or water in the solution, we know that 0.41 is the mole fraction, mass fraction of sulfuric acid, right? So that means 1 minus 0.41 is the mass fraction of water, right? Into 200. This is water in the mixture. All right. E is 60% of this water. So that is 0.6 into 1 minus 0.41 into 200. Right? 0.6 into 1 minus 0.41 into 200. That is 0.6 into 0.59 into 200. All right. Hope you people could get what I'm trying to say. Right? So the water evaporated comes as 70.8 kg per hour. How did we calculate? 60% of the water that was present in the solution. So water present in the solution is 1 minus 0.41 times 200, right? So 1 minus 0.41 is 0.59 and 60% of that is 70.8. All right, 60% of this is going to be 70.8 kg per hour. So this is what we have calculated. This is how we have calculated E. Now, once we have E, then we can use any of the two diagrams. All right, we can use any of the two diagrams. But anyways, since we already have this diagram, so let's use this itself. So we are going to use overall material balance. So we get 200 is equal to 70.8 plus P. Hence, we get P as 200 minus 70.8, that is 129.2 kg per hour. All right. And then we are going to do sulfuric acid balance. So sulfuric acid balance means 0.41 into 200 is equal to XP into 129.2. Now this is solvable. Now this is solvable since we have already got P from the above equation. So therefore XP we get as 0.41 into 200 upon 129.2. That is equal to 0.6347. All right. So I took up this problem because I wanted to show you that even if we have multiple units, it's not always advisable to use the main control volume method, the system boundary method. Because at certain cases, you will first of all need to do individual unit balances in order to get certain information, right? And then unnecessarily using the system boundary approach is of no use. All right, so this problem is a very important problem. So make sure that you're all clear with evaporation as well as mixing operation. All right. In the next lecture, we'll be dealing with distillation and further.